So today we're going to be talking about Schrodinger picture versus Heisenberg picture and quantum mechanics. And hopefully, if we have enough time, I'll start the discussion of simple harmonic oscillator. So we went over the Schrodinger versus Heisenberg picture in classical physics, where we could formulate physics in two different ways. One way was the state is time independent. Your observables evolve in time. We call this the Heisenberg picture. Equivalently, we could work in a setup where the states evolve in time and the observables are time independent. That's called Schrodinger picture. Okay? The same, actually, this terminology is quantum mechanical terminology, but I just wanted to emphasize that we could have done this in classical physics as well. All right, so what is the Schrodinger picture? Our kets evolve and our observables are time independent. So the equation over there, the time evolution equation as we derived is the Schrodinger equation for kets, right? So if you recall from your undergraduate quantum mechanics, sometimes people, when they talk about Schrodinger equation, they talk about the time evolution of the wave function in position space. That is precisely this equation when you take the inner product of it with ket x with bra x prime on the left, right? But the advantage of writing it this way is that it will tell you about how to view Schrodinger equation and an arbitrary frame and an arbitrary eigenbasis. Good. We said that the time evolution of the kets is given by an operator u2 prime. We call it time translation operator. We said it's unitary, importantly, right? And then we derived it as, in the case that this was Hamiltonian, is time independent. This is just the exponentiated version of e to power, is exponential of e to power of minus I h t over h bar. We said that Hamiltonian over h bar is the generator of time translations. So in the Schrodinger picture, as we said, observables are time independent. So you would be calculating the expectation value at calculated time t would be the same observable. Sometimes I put some S here to remind myself this is Schrodinger picture, Schrodinger observables, right? Calculated in a bracket where the ket and the bra are alpha of t. Now, we said that this alpha of t from this equation evolves by some u. Of course, the bra evolves by u dagger, right? So this expectation value is nothing but this expression. So now you should be able to see explicitly how to compare Schrodinger and Heisenberg picture, right? In the Schrodinger picture, the equation is always this. Oh, sorry. Yeah, no, that's right. This is always the equation. In the Schrodinger picture, we take this as the observable, and these guys act on the kets and the bras. The states evolve. In the Heisenberg picture, we package this whole thing and call it A h of t. Now, this guy evolves in time, and the kets are independent of time. Is that clear? Are there any questions about this? Right? It's all about what the evolution equation is pretty clear. It's about how you view it, how you want to formulate physics. They're equivalent at the level of this course. They're equivalent formulations. They actually are always equivalent. Sometimes certain things in physics are easier to do in Heisenberg picture. Is that good? All right. So I said this, but it's helpful to be a little bit more explicit. So in the Heisenberg picture, the observables are time dependent, right? And here's how they evolve, right? And the kets are independent of time. So I don't even need to put the T0 here anymore. Similarly, so this story that we just told was motivated by time evolution, time translations. However, we could have done this when we talked about space translations, right? Over there, we talked about a ket x prime, and we're acting with some spatial translation operator that we showed is e to minus I p over h bar delta x prime, right? P over h bar is the generator of translation, spatial translations. Here, we were working all in the Schrodinger picture, but we could have actually worked in the Heisenberg picture and said that the ket x prime is not evolving. What is actually evolving is your operators, right? So now you could talk about x being sandwiched with the translations from the right and translations from the left. Then you could expand this. If delta x prime is small, is infinitesimal, you could expand this relation to the first order. This you get x hat. To the first order, you get the commutator of p hat delta x prime x, and then higher orders. This was nothing but, anyone, what is this? What's the commutator of p and x? Minus I h bar multiplied by I over h bar gives you plus 1, right? So here I'm treating d of x infinitesimally. But in general, we're going to be talking about Heisenberg operators. To repeat, the Heisenberg operator is a Schrodinger operator, but sandwiched with the unitaries. These guys are time dependent, whereas the Schrodinger ones are time independent. The Heisenberg kets are time independent. So this is that manifestation. Any questions about the picture, Schrodinger versus Heisenberg? All right. So let's take a Heisenberg operator, and we said it's time dependent. Let's take derivatives of the Heisenberg operator with respect to time. Well, the Heisenberg operator is u dagger something time independent u. So the first derivative acts on u dagger. This is just derivative of multiplications, right? Then you have as of u. Then as is independent. So the next thing that the derivative acts on is the last u. So here's the equation. Now, if you recall, we explicitly calculated the time derivative of the evolution operator, time evolution operator. It was 1 over IH bar Hamiltonian u. If you take the dagger of that, you basically find the same equation with the order reversed, right? H is Hermitian, u dagger is here, right? And then you flip the sign. You go from 1 over IH bar to minus 1 over IH bar. Plugging these two relations inside here, you're going to learn that ddt of A of H is 1 over IH bar, the commutator of A hat, the Heisenberg operator, with the U dagger HU, right? Something subtle is going on here. So I want you to pay attention to this line. So up to here, everything I did was kind of like trivial. Well, it was just like simple plugging in, taking derivatives and plugging expressions with nu. Here I defined a Heisenberg Hamiltonian, right, as U dagger HU. If Hamiltonian is time independent, do I need to do this? When Hamiltonian is time independent, U is e to the power of IHT over H bar. So I'm dealing with this expression. Dealing with lack of chalk. So e to the power of IHT over H bar, H, this is Schrodinger, and this is Heisenberg, minus IHT over H bar. So what is this? What is this? This is just h of s. Why? Because this is a function of h and any of its functions always commute. So when your Hamiltonian is time independent, there is no need to define, to evolve Hamiltonian with time because it's independent of time. Right? So in the there's no distinction between Heisenberg Hamiltonian and Schrodinger Hamiltonian when your Hamiltonian has no explicit time dependence. However, if your Hamiltonian does have explicit time independence, these equations are no longer valid. Remember what we had for you was some sort of crazy Dyson equation or a time-ordered exponential. Once you have the time-ordered exponential, you're no longer allowed to, well, they no longer commute, so you need a Hamiltonian, right? You need a Heisenberg Hamiltonian that's different from Schrodinger Hamiltonian. This is very important because a lot of realistic problems when you start trying to calculate and do, you have to make sure that this step goes through clearly and you understand what is going on. When Hamiltonian is time independent, a lot of things are simple because you only have one Hamiltonian, it doesn't involve in time, everything is good. But in the Heisenberg picture, you have to be careful with your Hamiltonian. Another way of saying that is the following. What does it mean for your Hamiltonian to be time dependent? It means that it's not a constant of motion, right? So, yeah. At different times, you always have to make sure you get the Hamiltonian right. What is the Hamiltonian of the system? All right. But in general, the equation of motion, everything written in the Heisenberg picture is simply this. This is called the Heisenberg equation of motion. So I'm just going to pause for questions. Are there any questions? All right. So next, let's work out an example. The simplest example we can, and it's the example of a free particle. And we're going to get to the Ehrenfest theorem. So recall that the commutator of xi and pj is ih bar delta ij. This means that for any smooth function f and g, the commutator of x and f of p is just a derivative with respect to p of I. And for any smooth function g, the commutator of p and g is minus ih bar delta g over h bar. Do you see this, or do I need to prove it on the board? How would you prove it? Let me just sketch the proof. Let's say the first one. How would you prove it? Give me an example of a simple f of p, a simple one. Sorry? Just p is just obvious, right? You know the equation, but something more. P squared, okay. So here's p squared. How would you calculate this? What is this? This is this relation, right? So what you would like to do is you would like to bring this x from the far left to the far right. First, you write this term as the commutator of xp plus pxp p. So this is the first term, right? I still have this term. X hasn't gotten all the way here, right? But now this term, you know what it is. This is IH bar, right? So you got IH bar P, right? Plus, oh, sorry, what did I do? Plus PXP minus PPX. But then you notice this term is just P, X, and P. Which is what? Is IH bar again. So you end up with 2 IH bar P. If I look at the expression I had, my F was P squared. I take derivative of P squared with respect to P. I get 2P. That is the extra 2. And the equation is correct. You next calculate PQ. You find here, what do you find here? 3. P squared. You can prove this in an organized way. Then you take an arbitrary F, you Taylor expand it in terms of power laws, and then that's the formula you prove. Now, I did this having only one dimension, but the generalization to higher dimensions is straightforward. Similarly for G, you can do that. Right? So are those equations clear? They're very, very helpful identities, extremely helpful identities. If you ever, well, if you ever do the actual calculations, they save a lot of time. So one interesting thing that you learn immediately is that what is a function that's similar to its own derivative? Exponential. So if I put f to be exponential of p, it looks like the commutator of an operator with something exponentiated is proportional to that thing exponentiated. So remember this structure. Quantum mechanics, this is very important. Some operator A and some operator B, right? This would be well, actually, let me say the explicit, right? By that formula, this is what? This is IH bar, right? Del e to the power of p del p, which is e to the power of p. So what you end up with is a commutator of x with something that's IH bar that. Just remember this structure. It appears all over the place in quantum mechanics. I've already given you a motivation. I've already given you a motivation to talk about exponentials, right? Where did they come up? Translation operators, right? There were the exponentiated. So the spatial translations were e to the power of I p over h bar del x. That would mean that if I take derivatives here, I p del x over h bar, but the derivative will bring down I del x over h bar. Good. All right. We're going to be using these equations. Any questions about this? Those of you guys who have seen some group theory would recognize the structure. All right. So what's the Hamiltonian of free massive particle? It's just p squared over 2m, right? Classically, it's p squared over 2m. Quantum mechanically, it's p squared over 2m. So what is the rule? Going from classical physics to quantum mechanics, if my Hamiltonian, if I have my classical Hamiltonian, what did I do with the chalk? Whoops. If my Hamiltonian, what can go wrong? Actually, this is interesting. So I said going from classical physics to quantum mechanics, x and p go to become operators, and functions of x and p go to functions of x and p, right? In particular, Hamiltonian was an important thing, which we often take the Hamiltonian to be something along these lines. For free particle, as p squared over 2m, these are vectors, right? I'm just suppressing vector notation. Plus v of x. So when I make this a quantum Hamiltonian, then it would look like this. This is unambiguous, right? But for some operators, ambiguities come up. Can you see which? Can you give me an example of an operator where what I just wrote here is ambiguous and naive? Yeah, very good example. So if I on this side have xp, so my classical operator is xp, right? What is this quantum analog? You might be tempted to say, right, px. But then, well, this is a classical observable. I can write it as px. And if I did px, now these two guys do not commute. So these two are not equal. So which is correct? Which one is the right answer? There's this particular example is somewhat easy. You could come up with a fix. Can anyone come up with a fix in this case? Sorry? Average, you said? You would add them up. One way of doing it is saying take the average. What would be your motivation to do that? Very good, Hermitian. This is not a Hermitian operator. It's not an observable. What is the dagger of this? This. Right? This is, if you take the dagger of the top line, you get the dagger of the bottom line. So if you want to make it Hermitian, you just add the operator to its dagger. So in this case, it's so simple, you could fix it. However, in general, there's no simple fix. This is a crucial thing. It's a crucial concept in physics that the story I told, the story that Dirac taught us, you know, we take a Poisson bracket, you make it a commutator, is somewhat tricky. Turns out that in these simple setups, there's a mathematical construction framework choice you could make canonically and do this, but it's not always given. Okay. Good. So, but as long as for this course, we never run into these troubles, right? For this course, we're going to be talking about this type of Hamiltonians. So it's all good. Right? You can see that this is unambiguous. Right? Hopefully that's clear. Okay, so here's my Hamiltonian. That's why I can just naively write it down and hope for the best and see if things come out correctly. Good. So Pi is a Heisenberg operator. I'm going to make it evolve with time. ddt of Pi is 1 over IH bar Pi and Hamiltonian, right? That's Heisenberg equation. This commutator is 0. Why? I'm sorry, my P's and rows look very similar. This discussion has no rows in it. What's the commutator of Pi and Hamiltonian? I'm claiming it's 0. What is Px and Hamiltonian? Well, it's just that Px and Pi and Pj, they just commute, right? So of course this would be 0. You learn that from free particle, Pi is a constant of motion. Pi of t is Pi of 0. Any observable that is independent of time in the Heisenberg picture, we call it a constant of motion. This is consistent with the classical physics picture, right? In classical physics, momentum of a free particle is a constant of motion. It's called conservation of momentum. Next, we compute the time derivative of xi. Again, Heisenberg equation, 1 over IH bar is xi and Hamiltonian. Now, we just saw that. So how do you calculate this? Hamiltonian is, what is it? Is p squared, right? So I have to use that. Let me write it here. I have to use the identity I showed you guys. I have to, so my calculation is this. Say x squared, right? And the commutator is px squared 1 over 2m, py squared plus pz squared, right? This is an example where this is just f of px, py, pz, right? So I only care about the px part because x and py and pz commute, right? And you take the, I have to take derivative here. I have xi, so I have to take derivative with respect to pi, right? And what I find is that dxi dt is pi over m, but then we found that pi is independent of time, so this is pi of 0 over m. This example is so simple that because this guy is time independent, I can explicitly integrate the Heisenberg operator and write down the operator equation. Xi of t is xi0 plus pi0 over mt. So what you would have done in classical physics, everything about it, the solution to equations of motion, will go through quantum mechanically as an operator equation. This is a very, very simple example. Let's pause and see if we understand this. Yeah.
It seems to like quick introduction or
So this is an operator equation, right? It implies what it implies. You're allowed to use this equation inside your calculations. It does not imply what you said. We'll see that in a second. We'll see that in a second. Can anyone see already what is wrong with what he said? It's my next slide. So up to here, everything seems to be like quantum mechanics is behaving as if it's like classical physics, but that's deceiving. My next slide is this. Okay, there's something funky going on. Xi at time 0 and xj at time 0, of course, they commute. But would xi at time t and xj at time 0 commute? No, because we just solved for xi and there was p in it as an operator, and p and x don't commute. So what I end up with is xi of t no longer commutes with xj of 0. Can you interpret this in words for me? It means that I cannot simultaneously know the position of the particle perfectly now and tomorrow. That's what it means. You could turn it into an uncertainty relation because we saw that commutators give you uncertainty relations. This tells you about the amount of uncertainty you will have tomorrow times the amount of uncertainty you have today about the position of the particle. It has to grow with time. This is kind of wacky, right? It means that what you know about nature, what you know about the system gets progressively with time, it just gets worse and worse. Right? You know the position of the particle. You went inside the lab and measured the position of the particle. You prepared the particle over there, left it in a box, and left it. In classical physics, the idea is that nothing interacts with that system. If you come back tomorrow, a year from now, 10 years from now, the particle is still sitting there. Quantum mechanics tells you that as time goes by, it gets worse and worse. Your particle starts, uncertainty about your particle grows with time. So later in time, so like a second later, you're pretty sure it's in the vicinity of that point. A day later, you have more uncertainty. A year later, you have no idea where the particle is, pretty much. Right? It grows with t squared. Well, linearly in time, actually, because this is squared. So to interpret it is you localize the particle at t equals 0, but with time, the particle becomes more and more uncertain in position. That's just a statement that in the language of undergraduate level physics, the wave functions left to themselves, they just expand. This is a free particle, right? It's not interacting with anything. However, its wave function expands. This is just a very generic phenomenon. It's a consequence of the fact that because of the fact that position and momentum don't commute. Yeah.
All related to
Yeah, of course. Entropy would be a measure of uncertainty, so we could talk about entropy. That discussion is very nuanced, very complicated, but yeah, like entropy is. But let me actually relate it to something that you might be familiar with. You might have heard about, like how uncertainties in the classical rules grows, right? Like, for example, it's hard to predict the weather tomorrow. It's hard to predict the weather. It's much harder to predict the weather 10 days from now, right? That has to do with classical uncertainty, your lack of knowledge, right? Your lack of knowledge growing. It's not because like there's no, if I knew the position of every particle in the cloud and I have a powerful enough computer, I should not be able to have a problem predicting the future ever, right? That just means that today, the reason that it's hard to predict the future in classical physics is that our computers are bad. That's the reason. As we make better and better computers, we get better and better at predicting the future. But this is something else. This is a foundational, this is nature. This is just the way nature works. No matter how powerful a computer you have, you will never be able to predict the future. If you prepare the particle arbitrarily well, you knew exactly where it is, and you have an infinitely powerful computer, you will never be able to tell where the particle is in the future. And it gets worse with time. This is not your lack of like computational powers or like your shortage of computational power, the lack of like poor quality measurement. This is just nature. Nature simply does not, that particle does not have a position assigned to it at late times. Any questions? So you start seeing that we need to depart from the notion of classical reality. The position exists at all times. That gets very dramatic when we get to Bell's inequality. Bell's theorem. Any questions about that? Yeah.
expansion. Like is there an actual moment how it expands?
You can calculate it. How will you calculate? All right. What am I plotting? That's a very good point. I'm plotting the probability of finding the particle at time t at position x. Tell me what is the calculation I need to do that. So it's an expectation, it's a probability, right? So p of x prime at time t, it would be, we're in the Heisenberg picture, so my kets and rods are not involved in this time. Right? Now I have to put observable x at time t, right? Oh, sorry, I said you prepared some initial state. Sorry. You prepared some initial state alpha, right, at time t0, not equals 0. You look at the overlap with the x prime, that's the wave function position space, and you have to square this thing. This is the time t, right? What is that? Well, that is x prime, this unitary alpha t naught, well, unitary of t and t naught squared. So you have to describe to me first what was the state that you started with, right? Evolving in time, and look at the overlap. If you start at t equals 0 with that Dirac delta function, what is that Dirac delta function? The Dirac delta function at some position x double prime 0 means the ket means this ket. That's the state you start initiating with. So I have to put here x double prime or 0. Yeah. This is what you initiated. Here I'm drawing this at 0.0, right? You have to do this calculation. So we calculate that. Good. Do you have a guess of how it's expanding based on this equation? What is a wave function? It's a Gaussian. It's a Gaussian whose width that has a width that grows with time, like that. So the width of the Gaussian is that, right? It just gets wider and wider with t. But these are great questions. You just have to do the calculation for yourself to make sense of these, right? I absolutely encourage you guys. There's just so much. I can do certain calculations in class, but to make sense of these, you have to do calculations on the side. What is the actually? Let me say one more thing. If I take this operator, this equation, what is the expectation value? How do they want to say this? How do they want to say this? What is the expectation value of the x operator as a function of time? Yeah. It follows the classical trajectory, right? So for example, the example I gave you had pi of 0 is 0, right? The particle was sitting at a point, right? So if you look at what I drew, if you calculate the expectation value of the position of the particle, it's still at x equals 0 at later time. It's just that the uncertainty comes into the picture, right? So what happens is that a classical particle is localized here. As time goes by, it follows the classical trajectory, but its expectation value follows the classical trajectory. The wave function will start widening around that. We'll see that. That's actually exactly Ehrenfest's theorem. That's my next point. Is it clear that is the distinction between expectation value and the width of the probability distribution clear? Okay. Now, next, let's add a potential term. Yes.
So when you say to evolve like a classical equation, essentially x plus p by m into t.
X plus p is what, sorry?
P is the momentum.
Yeah.
P by m into t is.
Yes.
But we cannot know x and p at the initial time together because those still follow the uncertainty relation. So we technically can't write.
Correct. So you see, as an operator equation, this is what I wrote is correct. As an operator equation, I had this. Yeah, as an operator equation, that's correct. But this doesn't tell you that anything about the commutation relations, right? I can stick this inside expectation values, and I'm allowed to calculate expectation values, and I immediately see it follows the trajectory. But you're absolutely right. So here, what happened is this. At time t equals 0, x's commute, p's commute, and x and p don't commute. As time goes by, everything stops commuting with everything. Things do not commute. X and p, x at time t and p at time 0, of course, won't commute. But it's actually much worse. X at things that used to commute no longer commute. Right? That what you said is absolutely. But we'll see actually that, okay. Good, we're good. Now let's add a potential term, V of x. If I want to solve the Schrodinger, Heisenberg equation for evolution of operator P of I. So 1 over H bar, P, and I wrote V of x. What should I write here? I should put Hamiltonian, but I dropped the momentum part. Why is that? Because it commutes with Pi. Right? We saw that. That's the free particle piece. So all I'm left with is minus del xi V of x. This equation looks like the classical F equal ma equation. So there is an operator version of that, but these are operators, right? The thing that's interesting that's happening is that you're adding a bunch of operators. So you have an equation, you have F equal ma, F equal ma. Classically, everything is okay because these are just numbers, right? Quantum mechanically, both sides of the equations will have operators, right? What is dxi dt? Dxi dt is not changed compared to a free particle. Why is that? Because I added to the Hamiltonian V of x and V of x and x commute. All right, so now I can, this is an operator equation. I'm allowed to plug it in inside other operator equations. So here, I plug this inside this. I get the following operator equation. I get the second time derivative of xi. Notice what I'm doing here. It's very crucial that in quantum mechanics, t is a parameter. T is not an operator. X is an operator, right? I'm just treating t, of course, as a parameter. Is 1 over IH bar dxi dt of h. That's p and p over m. I plugged it in from this equation. It's 1 over m dpi dt, and it's minus the potential. So this is just the good old F equal ma equation, right, of Newtonian classical physics turned into an operator equation. If you take the expectation value of it, you get the Ehrenfest theorem. What does it tell you? It tells you that in quantum mechanics, F equal ma continues to hold for expectation values, right? But wave functions do crazy stuff. They expand, they do all. Well, the general rule of thumb is that uncertainties grow with time, right? We just saw that. All right, any questions about Ehrenfest? So the picture, the cartoon picture to have in mind is that the classical particle used to move around in some trajectory. Now, you could think of it as being described by wave functions centered around the classical trajectory. That's still a true statement, but that it starts expanding, spreading around the middle. That time goes by. Questions? All right, I'm going to introduce one more concept before talking about simple harmonic concept. This is a concept that's very, very useful in physics. It's sort of like a trivial concept, but the way Sakurai explains it, I find it somewhat confusing. I'll try, it's a very simple concept. I'll try to make it clear why they're saying it this way. But consider the old eigenvalue equation, eigensystem setup, right? You had an observable A acting on some eigenvector, gives you the eigenvalue. Now, this operator, we're gonna treat it as a Heisenberg operator, so it would evolve with time, and time evolution is basically sandwiches it with U dagger and U. So it's a legitimate question to ask, what are the eigen operators of this operator as a function of time. Do you have a guess? Well, I said I'm giving it to you. If A prime was the initial, were the initial eigenvectors, at later time, U dagger of A prime are the eigenvectors. How do you see that? Well, just plug it in. If this is an eigenvector, when A of H acts on it, this should give you something, which is the eigenvalue, multiplied by the eigenvector. So let's just do the calculation. A of H is U dagger AU. This is U dagger of A. U dagger is 1 because unitary. So you end up with U dagger A acting on A prime. This was just A prime, A prime. A prime is a number, you bring it out, you end up with this. You end up with this equation, which proves my point. It's an U dagger A prime is an eigenvector of the Heisenberg operator. Was this fast? Any questions about this? Yeah.
What was this called?
What was what called? Oh no. I've not said transition. What transition amplitude is? That was the this is a discussion to build towards transition amplitude. Yeah. I'll say what transition. Well, actually, this is transition amplitude. So the confusing part, I don't think it's confusing, but like if it's the first time you see it, you might find confusing, is that if you take this eigen operator, you could take a time derivative of it, and you find that it satisfies the Schrodinger equation with an extra minus sign. But I don't think that you need to worry much about this fact. It's just it's a simple, it's the same minus sign I picked up when in classical physics I was doing the phase space Poisson bracket, and I did the manipulation that brought the Poisson bracket from observables to the states. We almost never do this. All right, but this slide is important. So if A is an observable, will it remain an observable at later times? What does it mean that it's an observable? It's Hermitian. So the question is U dagger Hermitian operator U Hermitian? Take the dagger of it and see what you get. So you have U dagger A U. If it's Hermitian, it should be equal to itself. Its dagger should be equal to itself. So I'm going to take the dagger. How do I take the dagger of this? You basically reverse the order and take the dagger of them term by term. So this becomes U, bring it here, take the dagger. Then the second one in the middle, they take the dagger. This guy comes at the last, and U dagger, U. But because A was Hermitian, you end up with this. So of course, you learn that observables remain observables. That's good. That's sanity check. Right? So the observable, the Heisenberg operator at time t could be written as, ooh, there's an important typo here. Can anyone see the typo? The observable at time t could be written as its eigenvalues, which do not change in time, right? Multiplied by its eigenvectors, right? So eigenket and eigenbra. This is the basis that diagonalizes the Heisenberg operator. But these guys are just U dagger U and could be written this way. Now, we could talk about precisely this object. you could talk about something called transition amplitude. What is a transition amplitude? You start, let me write it on the board first. You start with, what is my notation, alpha? You start with some ket alpha at time t0 equals 0. Good? Everybody's with me? I first evolve this and then look at its overlap with something. What do they call it? A prime. This is called a transition amplitude. It describes the amplitude that this vector, this ket, evolves and ends up here. Good? This is called a transition amplitude. Now, all right, this is something that you could call, what is this actually? This is, okay, let me say it in two different ways. This equation, this transition amplitude could be interpreted in two different ways. You could think of this as you evolve ket, right? In Schrodinger picture, you end up with alpha at time t. You expand it in the A basis, you end up with C A prime T A prime. And this overlap is reading off this expression. Right? This is the Schrodinger picture. The Heisenberg picture says that this is your ket. You look at this guy, right? Your ket is fixed, but the observable A is evolving in time, and its eigenkets are evolving in time. You still interpret this. It's still the same expression, right? It's about whether you think of this, you interpret this equation as you act on the right or you act on the left. This is the difference between Schrodinger and Heisenberg picture. This is called transition amplitude. It's pre-self-descriptive, right? You transition from some ket alpha at time equals 0 to some ket A prime at some later time. It doesn't even have to be these. Some ket psi to some ket phi. This is called transition amplitude. It's the thing that if you take the norm of squared, the absolute value of squared, that's the probability for that transition. Questions? Because I think after this, oh no, yeah, I said this. Any questions? Because my next point, I'm going to change gears and talk about something a little bit. Yeah.
For the transition to actually, where should be in that state.
Yeah, you perform a measurement, and you end up in that. That's what we call an amplitude. Of course, the interpretation of this to connect this to the interpretation, you need to do measurements and stuff. Any other questions? All right. So in the remaining 20 minutes, I want to change gears and we talked about a free particle first, then we added a potential term and we proved the Ehrenfest theorem, which was the statement that the expectation value observable, the quantum particle, if you look at the expectation value as trajectory, it follows the classical trajectory. There's a very my next example is a simple harmonic oscillator. It's a special case of what I just described when V of X is just proportional to X squared, like a spring, right? A harmonic oscillator, simple harmonic oscillator, what we're going to do. Why? Why do we study this example? It can't be more true. This statement of Sidney Coleman, this quote by Sidney Coleman cannot be more true. The career, I would say, of a young physicist, not even theoretical, actually drop the young as well, is basically understanding the example we're going to go over in a million different ways. And I can tell you, I assure you that this could be understood in a million different ways. But if there's not a single week of my life that passes by almost shortly that I don't think about harmonic oscillator, this example is the most fundamental example that any physicist has in their arsenal. Good? Everybody's with me? So what are we going to try to study? We're going to look at a particle moving and a potential like this, V of x. What is such a potential describing? It's just like the particle is attached by spring to the center, right? That's what the potential is describing. If you find this picture confusing, get rid of the spring. It's just a particle attached to spring. And Hooke's law tells you that if the spring constant, I think they call it spring constant, K is K, that the equations look like P squared over 2M plus K, half KX squared, right? Why is that? Well, hopefully you remember class and harmonic class later. So we usually define the square root K over M as the frequency. It's a frequency. It has the right dimensionality frequency. And write the Hamiltonian as half M omega squared X squared. Here, notice that as before, there's no ambiguity regarding the Hamiltonian, so I can just write that. All right? So in this course, I don't know if you probably have seen this problem before in your undergraduate quantum mechanics. In this course, we're gonna solve this problem, solve this Schrodinger equation, and solve this system using a trick that is the trick I absolutely recommend you to think about. This is the most economical way of thinking about it. This is you save a lot of trouble if you think about it this way. What are we gonna do? We're gonna define two operators. We're gonna call them. So what are these operators? One of them is, let me first tell you what you should pay attention to. You have X operator, you add to it P operator with some imaginary component. And you put the coefficient here, M omega. And you put a coefficient out there. There's another way of writing all of this, which you might find it to be more helpful. How do I want to write this? I want to write it as that. I want to write it as M omega squared. Oh no, I'm on the H bar there. Yeah. M omega squared H bar X plus I square root 2H bar omega M. Is that up? No, M is down here. P. That's right. So sometimes you write it this way, sometimes you just factor it out. Okay. You define an operator A. It's called annihilation operator. If you watch a lot of the news and follow the war in Ukraine, so it's called lowering operator. If you're more peaceful. So the dagger of it is called creation operator or raising operator. Good. Yeah.
In general, what are quadratic Hamiltonian solvable?
That's a very well. Sorry. In general, quadratic Hamiltonians are solvable. That's a fact.
Yeah, why?
We were asking. Oh, because they're Gaussian. The solution is energy. Because you complete the squares. Because there's a trick that's called completing the squares. However, non-quadratic Hamiltonians are not always solvable. Sometimes they're solvable and they're using. All right. So A is not an observable. It's not self-adjoint. It's not Hermitian. Right? Nonetheless, it's a useful operator. So what are the properties of it? First of all, the commutator of A and A dagger is 1. This is a very, very useful property. These factors are there precisely to make sure that the commutator is 1. This is literally the reason. And the normalization. Okay, so that's property 1. You could check it explicitly, just expand it and check it explicitly. You could also define an operator called the number operator, which is A dagger A. So let me try to give you a set of words that might be helpful. If you're wondering about the meaning of all of this. Remember the phase space? X and P. What is my Hamiltonian? My Hamiltonian is P squared over 2m plus omega squared over x squared. What does that look like? It looks like something like this. If I rescale my x's and p's, I can make it a circle. The scaling is precisely that scaling. These coefficients I wrote down is the scaling that makes this as a round circle, right? So I just define some new x tildes and p tildes, multiplying them by the square root, blah, 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 such that this is just a round thing. Right? Good. What is my A and A dagger operator? It's a vector that points to a point on the circle as a complex vector, right? X plus, what is it? X plus IP. This is the imaginary direction. Is that complex vector, right? A dagger A is the norm of this vector, right? Just some intuition. If the story is a lot more elaborate, but if you're just first wondering what the hell, what are we doing? What are these coefficients? This is what the story is. We are using complex analysis tricks on the phase space. You could have done this in classical physics as well. Good. But now something funny happens. This number operator, A dagger A, it's an observable Hermitian, but it's a quantized observable. What does it mean? It means that we'll see in a bit that maybe in the next lecture, the length of this vector cannot be anything. It ends up being quantized. There are just certain lengths that are acceptable. This is analogy, right? This is just for you to orient your mind. I don't have to say any of these words, and usually none of these words are said when you teach this. Okay, so what is this n operator? A dagger A, you multiply them. You learn that this is m omega over 2h bar x squared plus p squared over m squared over 2h. You just expand this. You learn that this is 1 over h bar omega times the Hamiltonian minus half. So what have we done? We have taken the Hamiltonian, written it as h bar omega some operator n plus half. Okay? This operator turns out, it will turn out that this is not only an observable, but it's actually a positive operator. What does that mean? It means that there will be a minimum energy, which would correspond to half, h bar omega. Right? This is an afterthought. I'm assuming you have seen some version of simple harmonic oscillator before. The vacuum energy is half h bar omega. I'm separating that. Now, my energy is just a positive operator. Not just a positive operator, in this case, h bar omega and positive integer. Right? Now, this is a positive operator. I told you I can write it, I can always write it as q dagger q. That's what we're doing. It's a positive operator. The length of a vector is positive. Always. I'm viewing it as the length of a vector when I write it as a dagger. Any questions? So we're gonna work through this a little bit slowly, okay? Probably half of the next lecture we're also gonna be spending on this example. I think I want to make sure that this really clicks. Right? So I said this, but a priori, we haven't seen this yet. We're gonna prove this, but I'm telling you that this guy ends up having positive integers as in spectrum, which means that this is quantized, the length of this vector is quantized, Hamiltonian energy is quantized. In what units? Units of h bar omega. What does what do A and A dagger do? A annihilates a unit of h bar omega, we'll see that, hence the name, by shifting the eigenvalue by 1 of this guy by 1. A dagger will create h bar omega. Sometimes we call them raising and lowering operator because they're just increasing and decreasing the eigenvalues of this. So let's see. Those words maybe were too quick, but now we're going to go over it. First thing you notice that h and n commute. So they're simultaneously diagonalizable. Therefore, I'm just going to be talking about the eigenbasis of this n operator, number operator. It's called number operator. To talk about energies. And as I said, I promise that we'll get there. We'll see that the spectrum of this operator is just a positive operator with spectrum that's positive integers. By the way, if anywhere in physics, this is just like a piece of advice. Anywhere in physics, you see a bunch of integers appearing in the spectrum of a Hamiltonian, right? Meaning that up to constant, there's integers. This trick is useful. You must be immediately writing your Hamiltonian somewhere in this way. And hopefully I argued how to do it, right? You subtract the vacuum energy, you divide it by the unit of energy and write it as a positive operator, and then write it this way. These are very special systems. Physicists would call them free systems, but they'll non-interactive free, blah blah blah. Gaussian, maybe is a better word. I'm free. All right. Oh, I said this, that we'll see that the we're going to define, this is this eigenvalue problem. It will have positive integer eigenvalues and corresponding eigenvectors are n. This tells you that if h, these are energy eigenvalues, energy eigenvectors, and the corresponding energy eigenvalue is h bar omega n plus half acting on k. Right? So these are the energies, the corresponding energies. SHO is simple harmonic oscillator. Now, why are they called raising lowering operators? Let's look at the commutation relation of n and a. Well, this is the n is just a dagger a. You could expand this and write it as a dagger a plus a dagger a. This is 0. A dagger a is -1, so you end up with minus a. You could repeat this for a dagger and you get plus. It's a similar structure I hinted at before. I had two operators, a and b. I calculated the commutator of it, and the answer is proportional to b. This structure appears in physics in various places. And every time you see it, you should be alarmed. Why? Because if you look, because then these kind of relations relate the eigen operators they relate eigenvectors. They're nice construction in the following way. From these relations, it follows that A dagger n is an eigenvector of capital N. How do you see that? You take this n and write it as the commutator of n and A dagger plus A dagger n. The second term will just give you n A dagger n. The first term will give you plus 1. So you learn that A dagger n is an eigenvector of the number operator with a shifted eigenvalue, which is n plus 1. Hence the name raising operator. You repeat this with the for A ket n, and you find that the eigenvalue is still an eigenvector, but the eigenvalue is shifted by 1. So in summary, you have this table. Ket n is an eigenvector of number operator with eigenvalue n. A dagger n is still an eigenvector of n. Its corresponding eigenvalue is n plus 1, hence the name raising operator. Right? This is an eigenvector with eigenvalue n minus 1, hence the name lowering operator. You could say that they create A dagger creates one quantum unit of energy, H bar, call it creation operator and annihilation operator. That is more meaningful in field theory. In quantum mechanics, I think this terminology, I don't know, maybe it was left over quantum field theory. But. All right. Are there any questions about this? I'm going to pause here and summarize. The next lecture, we're going to finish this story, and we're going to spend a whole lecture on the properties of this n and a, the wave function, eigenvalues, eigenvectors, all of that. Because this is by far one of the most important things that you should learn from this course, right? So what did we say in summary? We started with simple harmonic oscillator. We wrote down the quantum Hamiltonian for it. It's just a classical Hamiltonian with x and b promoted to an operator. We noticed that we can write it in the phase space in this nice form as multiplication of h bar omega, a unit of energy. This has unit of energy. Hamiltonian has unit of energy, right? I take out the unit of energy. Then what's outside of it would be a number. So I want to deal with the number. Hence, that's why I'm doing this. That number, I'm going to write as A dagger A plus half. Right? And this A and A dagger are the operators I defined. The use of this trick was that you notice that the number operator in Hamiltonian commute, so I can use the eigenvectors and eigenvalues of the number operator to describe the energies and their eigenkets. This is the relation. Importantly, we learned that A dagger acting on an eigenket creates another eigenket with a shifted eigenvalue, shifting the eigenvalue by 1. That's why we call it the raising or creation operator. A acting on n reduces eigenvalue by 1, gives you n minus 1. From this formula, what is the ground state? The ground state is the state of minimum energy. Do you see what the ground state would be? The ground state is a state of minimum energy. It's a state that should be killed by n. This is again war terminology. That just means that n acting on the state that I'm going to call it as 0 should give you 0 times 0, which is 0. We say it's killed by it. Right? So this ket is going to become your vacuum, your ground state. Right? What is this energy? H bar omega half. Any questions? If not, thank you so much, guys. There is